Hey guys, it's Dora
and Raha,
and today's video is on
hydrolysis and the pH of solutions.
So today we're once again investigating the pH of various solutions. We've seen a few cases of acid-base hydrolysis in the first video, part 1. Let's look at some more solutions, see if we can develop our understanding of hydrolysis a little further. In this reaction here we have calcium bisulfite at 0.45 molar. It's amphiproduct, but Ka for the bisulfite ion is larger than Kb, so this will act predominantly as an acid, a weak acid, mind you. Let's look at the dissociation reaction for calcium bisulfite. It dissociates, giving us the two bisulfite ions. Each of those ions then reacts with water here in this fashion, giving you the hydronium ion and the sulfite ion. And this has got a let's just rearrange that and I'll make it a little bit nicer so it looks just like you see it on the data table. And if you have a look here, we now need to go and get the Ka value for this behavior here. And it turns out it's 1.0 by 10 to minus 7. So you can make an ice table, and if you do that, you get the Ka here, and just use the ice table in your imagination if you want. You wind up with X squared, that's the hydrogen concentration, and the sulfite. And down at the bottom, you get the initial concentration of bisulfite, which is, remember, it's a 2-to-1 ratio, so you get a 0.90 down there. We're going to say that X is quite a lot smaller than 0.90 here. There's 6 orders of magnitude between the acid dissociation constant and the concentration, so that's quite small. And here, solving for X, we've got the hydrogen concentration at 3.0 by 10 to the minus 4 molar, and the pH is a negative log of that value, and the pH there winds up being, if you're paying attention, 3.52. So quite a low pH. Let's look at the next solution here of potassium cyanide. Let me just comment on that one for a second. This one is very bad stuff. Potassium cyanide is exceedingly toxic, so stay away from it. But anyway, it does dissociate like this, giving you the potassium ion, which we know to be neutral, and the cyanide ion, which we know to be a weak base. So since this thing is going to be a weak base, we'll expect to have a highish pH. Here's our data table. We find the hydrocyanic acid, and on the right-hand side, the cyanide ion there acting as a base. It's going to react, gaining a hydride ion, or a proton, I should say, from water. So here we have the cyanide ion there reacting with water. It's going to gain that proton from water, making hydrocyanic acid, and of course releasing hydroxide ion. We'll need the Kb for this, which is Kw divided by K of the conjugate acid, which is hydrocyanic acid, and we knew that was 4.9 by 10 to minus 10 from our quick tour of the table there. So here we have the conjugate acid, hydrocyanic acids, it's Ka 4.9 by 10 to minus 10. So Kb is 2.04 by 10 to minus 5 for the cyanide ion. Again, I'm going to recommend you do an ice table, but just for the sake of keeping this short, we'll have it in your mind. They wind up looking pretty similar. Again, we'll have X squared here, where X is the hydroxide ion concentration as 0.65 minus X. Certainly X is quite a lot smaller than 0.65 here. We can say it's pretty, well, we're on the edge. There are 4 orders of magnitude here, so we'll just see. But certainly if you subtract X from 0.65, you should just get the same thing still. Little solution here for X on the simplified version. We'll get the hydroxide ion as 6.95 by 10 to the minus 3 molar. And you can see that the rule is working there. That value is small enough that it doesn't change 0.65. Anyway, the pH is 14 minus the pOH, and it comes up as 11.84. So on our next reaction here, we're looking for phosphoric acid. And go here to phosphoric acid. We saw that it was weak acid. So we'll go there and get the Ka value for phosphoric acid. Notice it's only the first proton coming off we're interested in. And the Ka value is the one we just got from the table, 7.5 by 10 to the minus 3. So again, use an ice table, and you wind up with this by now very familiar X squared over whatever it is, 0.0051 minus X. Now we can't make a simplifying assumption here because the concentration and the K value are quite close to one another. There are, I think, no orders of magnitude between them. So we would like to have 1 over 10,000 here, probably like 4 orders of magnitude anyway. And there's no 10 to the 4 orders of magnitude here, that's for sure. So we won't be able to do the simplifying assumption here. We'll have to do a full solution. So there we have the idea. We're going to solve this one by graphing, and we'll be graphing here. Ka will be the value we're looking for. And remember that Ka is equal to the reaction quotient Q when equilibrium is established. So we're going to graph here on the left-hand side. We'll graph the reaction quotient Q. On the right-hand side, we'll have X, which is going to be the change there in concentration of the hydride ion, and Q on the left. So we're going to be graphing Ka against Q, and where they're equal, then we're going to have the system at equilibrium. So here I'm pressing in the Ka value, and here we have the Q expression, x squared divided by 0.0050 minus x. We'll set a window. The maximum value is 0.005. Remember, we can't go any smaller than that, and the y max here will have 1 by 10 to the minus 2 to contain that value. So here's a graph, and certainly there we'll go intersect here and get the intersection at 0.0034. Let's just copy that one and put it into our calculation here. So there we have the Q graphing against Ka, and where they're equal, which is what we're looking for here, the point of intersection, we have, that's the value for equilibrium. So on your calculator, as I just showed, and you can do it by graphing, or you can do a quadratic formula if you like. We'll just do graph intersect, and there's our value at 0.0034. And that'll be the hydride ion concentration at equilibrium. So here we have it, hydride ion concentration equal X at equilibrium, 0.00343 molar. The pH, of course, is the negative log of this, and we get that the pH of this phosphoric acid is 2.46. Pretty reasonable. Let's look at oxalic acid, which is a weak acid, and it's also at a very low concentration here, and that thing has also, we think, a low pH. It's a strong weak acid in the sense that it's one of the more dissociative weak acids. So here we have the oxalic acid doing its dissociation. Let's read here and get the Ka for oxalic acid on your table. It's 5.9 by 10 to the minus 2. So again, a nice table. This is very familiar by now, x squared over 0.0025 minus x. Again, simplifying assumption does not work for us here because the concentration and K value are let me see here, we'll do the calculations. Turns out there's just 2 orders of magnitude there, and that's quite a lot more than 4 orders of magnitude, which is what we said we would be looking for. So again, we'll use a calculator here. It's just a reminder. We'll put these new values in here. This was for the Q value now. We'll put our K value, and we'll put our Q value into Y2 here. And just as a reminder, check that the values here are correct for your window. Can't be more than 0.0025, so you started with. And the maximum value here for the Q value will just go a little higher than what we were looking for. And here we have it. So we'll just go intersect and get x equals 0.0024. So there we have the hydride ion concentration, 0.0024 molar, and the pH is a negative log of this. Okay, so a couple of examples there showing the same thing. Here we have a pH of 2.62 for the oxalic acid. Anyway, that's about the whole story for now with hydrolysis anyway. Do stay tuned for our next lesson in Chemistry 12. Okay, so do stay tuned and have a look at our next lesson, which is an insert called Mixing Solutions of a Given pH.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.
Hey guys, today's Joe. Just kidding.
It's Dora
It's Hey guys, it's Dora.
and Raha.
And today's video is on
Hydrolysis and the pH of solutions.